Hi, my name is Peter Marek. I'm a graduate student at Indiana University, and today I'm going to be summarizing my research in mathematics. So broadly speaking, the area of math that I work in is stable homotopy theory with an emphasis on calculations. And the tools that I like to use the most are the atom spectral sequence and synthetic spectra. So in this talk today, I'd like to give a brief description of synthetic spectra because they are a newer construction, and talk about my own research with synthetic spectra, particularly my paper on the HF2 synthetic homotopy groups of topological modular forms, which you can find on the archive. Okay, so the basic idea of synthetic spectra, due to Pstragowski, is that synthetic spectra interpolate between the topological category of spectra and Hovey's algebraic category of E star E comodules, stable E star E. More precisely, how we would say this is synthetic spectra are an infinity categorical deformation of spectra with parameter tau and special fibers stable E star E. And we sort of think of this as a diagram below, where if you tau localize, or in other words, set tau equal to 1, you land in spectra. And if you take a cofiber of tau, or tau equals 0, you land in stable E star E. So more specifically, Pstragowski proves the following. If you have an atoms type spectrum E, then you have a stable infinity category of E synthetic spectra, which satisfies the following things. First, namely, synthetic spectra are presentable and symmetric monoidal, so you can do stable homotopy theory in them. Secondly, there's a fully faithful lax symmetric monoidal functor called nu from spectra to synthetic spectra, and this is called the synthetic analog functor. In synthetic spectra, we also have bigraded sphere objects, SKW, and bigraded homotopy groups for a synthetic spectrum X, with the unit being S00, and we refer to K as the topological degree or stem, and W as the weight. In synthetic spectra, there's an important map called tau between spheres and a cofiber sequence involving tau, as written here, with the property that the cofiber of tau is canonically in an E infinity ring. And if you look at the bigraded homotopy groups of cofiber of tau, you get certain X groups in E star E comodules, which happen to be the same as the E2 page of an E atom spectral sequence for the sphere. And for every integer in every synthetic spectrum, when you look at pi k star of X, this is a Z adjoint tau module. Okay. And then the general fiber of synthetic spectra, or in other words, the full subcategory of tau invertible objects, is equivalent to spectra. And we have a diagram like so that shows how it relates to nu. And for the special fiber, when you take the category of modules over cofiber of tau, this is equivalent to stable E star E, and you have a diagram like so for how it interacts with the functor nu. Okay, and then I want to briefly sort of talk about how you can do calculations in the synthetic world. So maybe an important question to ask is, well, what sort of information do the bigraded homotopy groups of nu of X for a spectrum X encode? And the answer to this turns out to be pretty much everything about the E atom spectral sequence for your spectrum X and the homotopy groups pi star of X themselves, and more information. So to say a little bit about this, let's look at the E2 page of the atoms spectral sequence for a spectrum X, which I'm using this notation for on the slide. And this converges to the kth homotopy group of the E nilpotent completion of X. Now, what an important paper of Berkeley, Hahn, Sanger in 2019, they show that if you have an element in the E2 page of the atom spectral sequence, which is a permanent cycle, so in other words, all the differentials on this element vanish, and it's not the target of any differential in the spectral sequence, then this corresponds to a tau-free element in synthetic homotopy groups, given in those bi degrees, K plus S. And secondly, they show if you have an element in the E2 page which is the target of a differential, then this corresponds to tau to the r-1 torsion in synthetic homotopy in that given bi degree. So this is important because the tau to the r-1 torsion is how we keep track of differentials synthetically. That is the mechanism. And we also have interpretations for hidden extensions in synthetic homotopy theory. So via the tau inversion factor. Namely, if you have a hidden relation x times y equals z in pi star of x that jumps by a certain atom's filtration, then this is the same thing synthetically as a relation x times y equals tau to the a z in the bi-graded homotopy groups. And you can do this for relations with more terms and various filtration jumps. In particular, if we look at the two complete sphere and we have EBHF2, we have this relation in pi 9, where the first two terms you see live in filtration 3, but the last one lives in filtration 4 in the atom spectral sequence. So synthetically, the way we account for this is we write it as we write it the same, but we add a tau for the filtration 4 part, the eta epsilon term, because it came from one filtration higher. So that relation synthetically is telling you that it's keeping track of the information that eta epsilon came from one filtration higher. Okay. And now I'd like to talk about my particular research in this area. So the motivation for the calculation I'm going to talk about, which is new of TMF, is that in one of the more complete synthetic homotopy calculations, see what additional things are going on synthetically. And we know the classical atom spectral sequence for TMF, the two complete TMF, entirely thanks to work of Bruno Ragnes. So this would be a great candidate to study more about synthetic homotopy. So the process goes as follows. So you start with the cohomology of TMF, which was calculated by Hopkins-Mahowald, written like so. And then you can describe a certain synthetic spectral sequence with E2 page written like this, which is essentially the classical E2 page for TMF with a polynomial tau generator joined. And then this atom spectral sequence that you perform, or the classical atom spectral sequence for TMF, turns out to only have D2s, D3s, and D4s. So synthetically, what this means is when you get to the E infinity page of your calculation, it's going to look essentially the same as the classical one, but now you're going to have tau squared and tau cubed torsion added on top of the classical stuff. And then to compute various things about the multiplicative structure on synthetic homotopy groups, we have a range of various tools, which I'll just have listed here if you want to read more about them. And my main results is I show that if you look at the analogs of 2, eta, and nu synthetically for this calculation, you can compute all of them in the periodicity range for TMF from 0 to 192. And to end this talk, I will just show a few slides to see what you get. So this is from 0 to 32. From 32 to 64, you start to see some sort of braided patterns appearing, and these continue as you go on. And that's all I have. So thank you.